Well, hello and welcome to the first of two videos that's going to be focusing on the relationship between electric field and electric potential. I'm breaking this up into two, even though they're really just inverse processes of each other. I think it helps to practice them separately. So we're going to start with the idea that we know something about an electric field, and then we're going to try to figure out something about the electric potential, or potential difference, we usually say. This is kind of the order that most textbooks present it. So you spend a chapter or two, or in the case of Dr. Knight's book, we spent 3 chapters, 26, 27, 28, just focusing on understanding what an electric field is. But in practical terms, it's not all that convenient to know stuff about the field because they're just really hard to deal with. They're hard to measure, hard to do much with them, and so what's much easier to deal with is knowing something about electric potential. So let's look at the connection between them in the easiest situation, and that is when the field itself is uniform. So I have here the most common way to get a uniform electric field, and that is a couple of parallel plates. We refer to it as a parallel plate capacitor. And I'm going to imagine we have an electric field in there of 250 newtons per coulomb. And what I'm going to try to do is to describe the potential difference between any two spots within that field. So I could imagine maybe here in green I'll mark a starting point. I don't know, maybe my starting point there at that point, and then I end up somewhere over here at that point. And I want to know what's the difference in the potential between those two locations. So I'm going to derive here briefly, I don't want to spend a lot of time on it, the connection between the field and the potential. And I think what's important to remember is in a previous section we talked about potential energy. And so potential energy, or potential energy changes, can be calculated by imagining moving a test charge through an electric field across some distance. And the product of those three values is the amount that the potential energy changes. And then we have to remember that it gets lower if we move with the field. So if we take our test charge and move it in the direction of the field, or at least partially in the direction of the field, is when it's going to get lower. Well, we define potential difference as just the potential energy difference per charge on our test charge. So we're just dividing out that Q. And so we're going to get E and D left over. But because we get lower as we move with the field, it helps to incorporate the angle business by saying if we treat each of these as though they're a vector, which is perfectly fine because the field is, and the D we could just think of as a displacement, then instead of just regular old multiplication, we will do dot multiplication of vectors and put a negative sign on the front, and that actually takes care of everything we'd need to do. So let's imagine doing it in this case here. If we want to know the potential difference between those two locations, then we could imagine drawing a displacement vector in green. I'll just draw it like that. And then we have to take the dot product between the field, 250, and that displacement vector. And then the dot product says we use the cosine of the angle in between them. But notice the shortcut here. Because the dot product is only going to give us a measure of the parallelness between the field and the displacement, that means we only really need to know the displacement that's in the direction of the field. So if we pull a ruler down here, we say, well, how much displacement do we have leftward? That's 6 centimeters. So the 6 centimeters would be our displacement times the cosine of the angle. We kind of incorporate all that into just one number. So 250 newtons per coulomb times, I'll convert this to meters, 0.06 meters. And we get 15, and that will be in units of Newton meters per coulomb or volts. I have to put the negative sign on there, don't forget that. So the potential difference there between those 2 points. But because it's a nice uniform field, then we could also say we would have gotten the exact same amount of potential difference even if my second location had been up here. So it's really all about what vertical line you're on in the case of this horizontal field. So what we often do is we just describe what those potentials are. We call these dashed lines here equipotential surfaces. Between each one is only 2 centimeters. So each one has 5 volts of potential difference between it. Now, a lot of times it's arbitrary what we call any particular potential because we're really only concerned with differences. But it's very normal to say that the lowest point anywhere on our arrangement will be called 0. So I'll write it here in blue. Let's just say this is 0 volts. And all we know is that that has to be the very lowest point because we always get lowest potential when we go in the direction of the field. So since I'm going to move rightward here, I have to be getting higher numbers. And each of those 2 centimeter lines, the space between them, is going to be another 5 volts. So we have a 5 volt line here, and then a 10 volt line, 15 volts, 20, 25, 30, and then our positive plate here would have to be at 35 volts. So we call these equipotential lines, those red dashed lines. They have an important characteristic in that they are always going to be perpendicular to the electric field, and they are always spaced out when we draw them by the same amount of potential difference. In this case, it's 5 volts per line. So once you have it drawn like that, it's awfully easy to tell very quickly how much potential difference you have between any 2 points, because if I move my second location here, that's just 1 line over, and that's really easy to see that I am 20 volts lower there. If I move it back to here, I'm 5 volts higher. Oh, I said that wrong. It's 5 volts difference lower here and 5 volts higher here. So lots of things we can do once we have that mapped out. Now let's look at a slightly more complex situation, and that is if we don't have a nice uniform field. So I picked probably the next easiest situation, and that is if we have a nice point charge creating a inverse square field. We radiate out from the center of the charge. You can see those field vectors there, and I've just said perhaps that field is 20 over r squared. I'm used to writing kq over r squared. Well, maybe kq is equal to 20. So what's the potential difference there? Well, if you notice, you can't work as simply as we could before, because before what we said was we're just going to multiply the E times the displacement. But the problem is our E is not just a number. Our E is a function that changes with our location. So as soon as we start to change our location, we've changed our E. So we need to use a clever form of multiplication that allows us to deal with this changing field. And that clever form of multiplication is known as integral calculus. So I'm going to write the same equation in a different form. And I'm going to say we're just going to find a small, tiny little change in potential difference between 2 points that are so close together that we can approximate the field as being uniform across that. So then we'll say E, and we're going to use not D for our little step. We're going to talk about a radial motion here, so we're going to use R instead. So a tiny little radial step towards or away from that charge we refer to as a dr. Okay, now the D again is being used in the calculus form of D. That means a tiny, tiny little delta. And the R is being used as kind of our displacement vector. So if we want to get the entire potential difference across maybe a lot of those steps, we sum together all the little small changes, and we sum together this side over here, and then we have an expression that's going to be much more convenient. Not easier, certainly, but I'm going to even write it as my dot product in case we have some angle business to deal with. And what this means is we perform an integral of the electric field function with respect to whatever the displacement vector is. And we usually need to put some limits on these integrals. So we'll have some starting position. I'll just call it the initial position, r sub I. That came out kind of ugly, so I'm going to rewrite it. R sub I. And our final position we'll call r sub F. So what would that look like in the case of our field here? Just to give you a practical example, let's imagine we go through this field, and we want to find a potential difference between any two particular points. I won't necessarily specify those points. Whatever they are, we would go here for our limits. We're just going to plug in the function for our e, so that's 20 over r squared dr. And hopefully you know your calculus well enough to be able to perform that antiderivative. That gives you 20 over r and a negative. That's the antiderivative. I always write mine in these little brackets. And then I evaluate that antiderivative at my upper bound and my lower bound. And I'm going to get negative. Actually, I'm going to cancel out these two negatives. That's kind of nice. So I'm going to get 20 over my final position minus 20 over my initial position. We could certainly write that a little differently, but now we've taken into account the direction. Remember, we canceled that one out. So for this particular electric field, this might not be the same as every point charge you ever see. It's just that 20 over the two positions and subtracting them. So there's an example, but what I want to point out to you is you may have functions that are different. So the most important relationship I want to show you here is this one, because it's going to be used for any particular function you have, as long as it's not uniform. Now, if it is uniform, you can still use that, but I think it's a little bit of overkill. So, all right, we are approaching 12 minutes here, and I don't like to go that long, so I'm going to let you stew on this for a while, look at some specific examples, do a little more poking around for some assistance if you need it. That always includes me in the classroom. So good luck.